start singing? Nice. So multiple stereocenters. If we have multiple stereocenters, now we have multiple possible stereoisomers coming out of that. So a popular question is just to ask how many stereoisomers are possible for an individual structure. And where that comes down to is just then looking at a formula where it's 2 to the n, where n is just the number of stereo centers within your individual structure. And that can help you find how many total stereoisomers. So if you were given the question like we walked through on Wednesday of trying to draw all the possible stereoisomers of this structure, you might think, oh, I've got a whole bunch to go through and draw, and you may end up duplicating some if you go through it just kind of randomly. Right? If you determine how many stereoisomers are possible first, when you start to draw them out, you can be like, oh, I have 4 structures, I'm probably fine, I've probably covered all my bases. If you start to draw 6, then it's okay, I've probably overshot and I'm duplicating structures through it. Okay, so it's all about trying to keep it as organized as possible. One of the issues that we talked about with that previous compound with the dichlorocyclopentane is that if you have an internal mirror plane, you lose a stereoisomer. And that's because the structure ends up being identical to one of the other quote-unquote stereoisomers. That is a result of it being a meso compound. Okay? And a meso compound is merely something that is identical, but we're adding a little bit of extra information to it. We're saying that it has at least 2 chiral atoms. So the molecule has that aspect to it. If it does have that aspect to it, then we go through and call it meso as opposed to saying it's identical. Okay? Because the relationship is identical, ultimately you lose a possible stereoisomer if you have that plane. Okay? More commonly where this question is asked is if we give you some random big structure and we ask for the total possible stereoisomers. Because everybody sees a big structure, panics, freaks out, and assumes that the question is impossible. Okay? And you kind of lose sight of what you're trying to do. So when we're trying to find our stereoisomers, we just need to know how many stereocenters there are. Well, in finding stereocenters, what did we need to find? An atom with 4 different things attached to it. So when you look at this structure, where's there an atom with 4 different things attached? Carbon to the left of the nitrogen. So we've got 1 there. I only see 3 though. Okay. Again, your hydrogens will be implied. You have to remember that they're there. Okay, particularly in stereochemistry. Where else is there a stereocenter? If we go further to the left, we have another one. So in this case, we have 2 stereocenters. N equals 2. How many possible stereoisomers can we get? 2 to the 2, which equals 4. Is it possible to draw an internal mirror plane in this structure? No. Okay. Most commonly, when we give you these big, fancy, crazy-looking structures, there is no internal mirror plane, so you end up with 4 stereoisomers. Okay. This is also one that I probably would not ask you to draw all the possible stereoisomers, because it's going to take you forever just to draw the bulk of the structure without even evaluating the stereocenters. Okay. So we're going to go through and spend the time to actually turn this into a quiz. Okay, so if we take a look at that first structure up on the left, I've gone through and highlighted, dotted our 2 chiral atoms with big red dots. Most commonly, you'd be asked to on an exam to star them. So we could go through and star, same deal. Okay? Yes?
So just 4 bonds, but they don't have to be all different atoms?
So this gets back to our question on what different means. So when we talked about it before, I keep kind of oscillating between different and distinguishable. Okay? Because ultimately there's a connotation with different that you assume it has to be a different atom. It's not officially that definition. Think back to identical versus different in our flowchart. Okay? If our structures didn't superimpose outside of class, we might say they were different. Inside of class, we call them something else. Okay? So different does not mean an entirely different type of element. It means, is it distinguishable from another type of element next to it? Okay? So let's take a look. Let's Let's go ahead and we'll call that one our blue atom there to look to see what its four distinguishable groups are. Number one, I only see three things. What's the fourth? Okay, there's a hydrogen. Where is that hydrogen aimed? Away from us, it's got to be the dash. Okay. Now the part that some people have been tripping up on, okay, identifying if they're different or not. So if we go through, we got the hydrogen versus carbon. Are those different from each other? Yes. Okay, everybody seems to be okay with that. Then if I move further out, I get two carbons. Okay. Blue is a horrible color. Let's try purple. Does purple work better? Is this carbon different from this carbon? That's an interesting statement. I was actually expecting most of you to say no. Okay, but you're saying those two are different. Let's accept that. This carbon different from this carbon? No. Yes. Okay. Yes. Yes. They are different. So this is why I expect you to say no with this first one. Okay? Why are those two different from each other? Okay. So what it appears to me you're all doing is you look at that and you say those are definitely different from each other because the atoms connected to them are different. But when we now go through and add and compare here, are you telling me that the atoms connected to both those carbons are exactly the same? They're different. Okay? That difference may not be obvious. Okay? That difference may be several steps away. So what we end up doing in each of these cases is we check to see if there's a difference immediately. Carbon versus hydrogen. Is there a difference in the atom? No. Between carbon and hydrogen? Yes. Between carbon and carbon, is there a difference? Okay, no. So in our first case where we compared these two carbons, we say there's no difference. So we move one atom further away. Okay? In the case of this guy, we go out to a hydrogen. In the case of the other carbon, we go out to carbon or oxygen. Is there a difference between carbon, oxygen, and hydrogen? Yeah. So we see that difference pretty quickly. Okay, so you acknowledge that we then have at least two different groups. I'm just going to number them horribly right now. Those two are different, and then this guy's got to be different as well. Right? What happens when we now include this carbon? We see no difference right away, so what do? We go to the next atom. We go out to hydrogen. Is hydrogen different from hydrogen? No. So what do? We go back to our carbon, and we go back out again, and we find another hydrogen and another hydrogen. Is there a difference? No. So what do? We go back to our carbon, and we go out to the next atom, carbon versus carbon. Is there a difference between carbon and carbon? No. No. So what can we go through and do? We go out to the next atom, hydrogen versus oxygen. Is there a difference between oxygen and hydrogen? Yes. That means that my blue circled carbons are different from each other. That then means my purple carbons are different from each other, which means I now have four distinguishable groups, which means all of that work, and really all I got out of that as I erase everything, is that that is a chiral carbon. Okay? Your differences may not be obvious. You may want to go through and write out all of that work. You may not. That's up to you. Eventually, you need to be picking up these differences very quickly and internalizing that differentiation mechanism. Okay, so that you can see where you have chiral carbons. We'll run into a similar issue here. We've got another chiral carbon. Okay. So now, or actually before we do that, questions? Nothing? Just depression? That's always fun. Let's compare between these two. Okay. So what things changed? What could we try and do as our first comparison? Okay. Okay, so we could go through that flow chart and we'll follow it all the way down. Eventually we'll get to, what is it? I already forgot my flow chart. We'll get to stereoisomers, right? Okay. Then what's the question asked? Okay, do we have chirality? Do we have chiral atoms? Yes. Next question. Are they mirror images of each other? Okay. This can be difficult to see, but let's look at a quick shortcut for this one. If we take the mirror image of my left hand, what do I end up with? My right hand. If I take the mirror image of a dash, but then maintain the structure, what do I end up with? A wedge. So what happened to this OH? Or sorry, that bond? Are those mirror images of each other? Yes. Okay. So those two are mirror images of each other, which suggests at that position, only that position, that we could potentially be looking at enantiomers. Just a second. Or actually, let's go ahead.
But wouldn't it then be on the other side of the structure?
So it depends on how you want to set up your mirror image and where you draw your mirror plane. Okay, so let's go through and draw a mirror image of this. So if I draw this mirror image, what's the closest thing to that mirror? I would change that around a little bit. It's not the OH, it's the HO. Hold up. Everybody agree on seeing this mirror image?
No.
Okay, what's the no?
You have a wedge.
All we're doing is directly reflecting. If I put a mirror image right here, okay, or a mirror plane right there, if my thumb is pointing out on this side of the, if my thumb is pointing out on this side of the mirror, where is it going to be pointing on the other side of the mirror? The exact same direction, pointing directly out. Okay. Why were we talking about this wedge dash issue? If we tried to superimpose these structures, would they superimpose? No, the carbon structure doesn't superimpose. Our double bond's in the wrong spot. So what do we end up doing to this structure? We rotate. Okay, about our, I think I'm going to regret doing this, our axis straight through the middle of that. If we do that rotation, what happens? The double bond's now on our left side. What happens to the OH? Where should it be, on the left or the right side now? The right side. Should it be dashed or wedged? Why is it wedged? Okay. I turned the molecule around. It was dashed, aimed away from you, but then I did a rotation. It's now wedged. What happened with the bottom one? It should be dashed. And then we're just drawing that as an OH. Go back to that OH that we were evaluating before. It was dashed and it ended wedged. If we change the orientation of it, it ends up becoming the mirror image. Okay, so if we switch from dash to wedge, but we maintain our carbon skeleton, we've done the mirror image at that position. Okay, so I'm only looking at that position right now. So for the top half of the molecule, we're looking at a mirror image. What happened to the bottom half of the molecule? Okay. If we look at the mirror image, we would have to go through and see that dash bond. Is that what we see in the other structure? No. What do we see in the other structure? A wedge. Are we looking at the mirror image at the bottom of the structure? So the top is a mirror, the bottom, oops, drawing that in the wrong spot, sorry. The top is a mirror, and the bottom is not a mirror. What does that mean? They're diastereomers, because our structures are not mirror images of each other. Okay? So our shortcut can be look at your chiral atom, be it wedged or dashed. If it changes its orientation in space, we're looking at the mirror image. Okay? If I look at my left hand and I do the mirror image of it, and my thumb is aimed to which direction? Right now? Your left? Okay, I was figuring it out. We look at the mirror image, what happens to the thumb? It's aimed to the right. Right? We've changed the orientation of space with my thumb when I look at the mirror image. So if we look at a chiral atom, we can see that switch to wedge to dash. That can help us trigger that, hey, we're looking at a mirror image. This also assumes that we locked the structure in place and that we haven't done any flips or rotations. Right? If we go through and look at the other one, what happened? It went from wedge to wedge. Did I change it? No. Which means it's not the mirror image. So we can attempt to evaluate those subtle changes to try and interpret relatively quickly without having to draw out a mirror image and then rotate it so that we can get it into a superimposable format to do all those interpretations. Okay? They're sort of shortcuts that you pick up as you do enough practice. Okay? In general, what I would recommend doing is you draw the mirror image. Okay, that's what we've got in blue. We drew the mirror image, and now what I want to do is see, does that mirror image superimpose on the other structure? Does it superimpose? Okay. Does the blue structure directly superimpose on my right structure? No. Okay. We have some carbon mismatching, though, so what do? We do a rotation. Okay. What's the relationship between this blue structure and the red structure? What's my name? What's my name? Backwards mine. Okay. So it's been the same thing. It's these two are identical structures. And I know this blue one is the mirror image of this one. Okay, so if I now take the red structure and try and superimpose it across, if these two structures superimposed, what does that mean? Those two, red and black, would be identical. Right? And since I know the relationship between red and blue is enantiomers, that allows me to then drop in more interpretation over the top. Do they superimpose? No. So they cannot be enantiomers. At that point in our flow chart, what's our only choice? Diastereomers. Or disasteromer, I don't care. Right? So, relationship here. What's our relationship top to bottom? Okay. You guys did that awfully fast. What trick did you go through and pull? What did we do to that bond? We switched it. We did the mirror image. What did we do to this bond? We did the mirror image. We did the mirror of both positions, which means it's the mirror image. Are these structures superimposable? If we tried to overlay those directly on top of each other, they don't superimpose, which means we're looking at enantiomers. What's the relationship between these two? Okay. Can they possibly be enantiomers? It is physically impossible because we've already established that up here, those were diastereomers. Okay, so we have to be looking at diastereomers here. Okay, so in these type of problems, some people are exceptionally good at manipulating these structures and can see all those spin flips and rotations and mirror images in their head. Good for you. Okay. For those of us that aren't, what you should do is simplify your question down. So if I want to see the relationship here, one of the things that I'll do first is look for that superimposability, because that's one of the most important aspects in identifying relationships. Are they superimposable? Okay, these are non-superimposable. Nice, because it was actually drawn directly for us. Okay, so we could overlay the carbon backbones almost instantly and see that our bonds aim different directions. The next part is dealing with mirror images. Up to you how you want to do it, but I usually show a dotted line, and I go through and directly reflect through this everything that happens, or everything that I see on the other side. The problem with this direct reflection is that, do I now obviously see the superimposability with the structure below? No, because the carbon structures don't overlay. So what do you typically end up having to do? You have to do a rotation. Let's just call that a rotation. I just spelled it wrong, that's all it was. If we do that rotation, we end up here. Are those two structures superimposable? Which means these two structures are identical. What was the relationship between these two structures? Identical. Let's use our fancy words. What was the relationship between these two structures? A little bit more than that. There were enantiomers, not just mirror images. Right? What does that then mean about the relationship between these two? Logically, they have to be mirror images and they have to be enantiomers. Lots and lots and lots of drawing. It's one of the reasons why I hate this section of material, because I can't see it and I have to draw it out a million times. Some smart student is going to come up to me and, what's the answer to this one? And I'll draw it out and spend 20 minutes to draw it out. And they'll be like, whoa, 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 I got it halfway through. Thank you. I appreciate that. Right? It takes time and practice to go through and draw them out. You just need to get used to that habit of drawing them out. Accept that it will take time. Draw it. Stop doing the manipulations in your head. Okay? Questions? Identify if the molecule can be chiral by marking all stereocenters and determine the possible stereoisomers. Okay. Take a look, see what you can come up with. This is a little bit easier because we aren't asking for relationships. We just want to know if it's a chiral molecule or not. Which two are chiral? First one and the last one. I don't know why I wrote last. That's chiral. And the middle one is technically called achiral. All right, where's our chiral atom in our first structure? We've got our wedge dash carbon. In our second structure, why does that one get tricky? One of the big red flags for chirality that you tend to look for would be wedges and dashes. What do we see in that second structure? A big honkin' wedge. So we might say, oh, well, that's a chiral atom, okay, or a chiral carbon. It's not chiral because what do? We go through and evaluate. Is there a difference between CH2 and CH2? No. So we move one atom further away. Is there a difference between CH2 and CH2? No. What happens? We now meet in the exact same point. Can a point be different from the point? No. Which means are the CH2s different from each other? No. How many different groups do we have around that molecule or around that carbon? Only 3. Okay. So we haven't satisfied our limit. On the last one, how many chiral atoms?
2.
Everybody agree? We got 3 of them. There's no double bond in this case. So that methyl group up top, that carbon, ends up being a chiral atom as well. Okay, so it's a question of trying to trigger these as quickly as possible. How many possible stereoisomers for the first one? 2 to the 1 is 2. For the second one, 0. And for the last one, 2 to the 3, which gives us 8. Okay? Exciting. You can laugh, that's okay. Questions? So we have a CH3, hydrogen, and we have a CH2 and a CH2. Can you tell a difference between those? Not at that point, so what do? CH2 versus CHOH, however you want to list it. Is there a difference at that point? Yes. What does that mean? The two blue CH2s are different from each other as well.
The foot kind of goes into putting splitting in each side to mirror each other.
So one of the things you can attempt to do is look for that internal mirror plane. So if you're trying to distinguish between two groups, what the book is suggesting you go through and do, we clean that up a little bit, is that we draw a mirror image, or we look at the mirror image running right through here. Is there a difference on each side of that? Yes. That OH is clearly different, which means these two carbons will also be different. Okay? Sometimes it's obvious, sometimes it's not. It ultimately comes down to practice, and when it clicks, it just clicks. Yes?
So on the first one, there's only one chiral atom
Yes.
going down it. It doesn't meet that same criteria for with that double bond. It doesn't meet that same criteria for different atoms.
Yeah. So what I think I know what you're saying, is what we'd be doing in this case is finding the slice. This is not going to look pretty, but I'm going to attempt to do it. Our mirror plane. Is coming in and out of the board, cutting the CH3 and the H directly in half, and you're now comparing this half to this half. Okay? They are different, so we do have those two carbons being different. Kind of makes sense?
But there's only one chiral atom.
There's still only one chiral atom. So now we're going to kind of bounce through a bunch of math and stuff like that I really don't want to talk about, and I'm probably going to relegate to just having you guys look at it in the textbook. Sort of. We can make some physical observations of these molecules. So if you go through and run a reaction where you produce two products where they are mirror images of each other, right, that means they have the exact same bond connectivity, which means their physical properties are exactly the same. If we go through and look at generating two products that are diastereomers of each other, what happens with their physical properties? Okay, so what we've got in this case is two products. We're looking at the trans methyl and the cis dimethyl cyclopentane, and we're looking at, again, our trans and cis here in kind of a Hayworth projection. Did we talk about Hayworths? Okay, just wanted to make sure. Okay. In the initial drawing setup, it may not be apparent that they have obviously different interactions, but when we switch to the Hayworth, do we see that they have different interactions? Okay. That should drastically change how the molecule interacts with other molecules. Okay. We could almost get kind of a chair stacking system here. Okay, whereas the other one, we're going to run into odd arrangements of those methyl groups through our stacking process. Well, if our stacking varies, what happens to our intermolecular forces? They also vary, which means if we take a look at the physical properties for a pair of diastereomers, we're going to have different physical properties. Okay, exactly different. Which would be kind of neat, because then I can separate them based on boiling points. Okay? Or TLC, or column chromatography, all of those kind of standard techniques that we would go through and do in the lab. That allows us to separate it. Okay? Yeah?
Would you be able to assume that the physical properties are going to be different based on the difference in energy?
It ultimately can come back to a difference in energy between those two conformations, yeah.
Or does that not necessarily, if they're different energy, then
I
necessarily have different?
I would avoid bringing energy into it. I think it's complex enough. I would just look at the structural implications of it, saying that they have different structures, so they're going to have different properties. How could you identify which one you had made or isolated? This goes to everybody in lab. Everybody in lab has learned 2 identification techniques. You can do melting point, and you can do TLC. A couple of people have mentioned recrystallization. Recrystallization is not an identification technique. What does recrystallization do? It purifies. So if I had 2 of these compounds in a mixture, I could recrystallize it to separate one from the other. How would I prove that I've separated one from the other? Then I can do melting point. 2 separate concepts, 2 separate techniques. What happens if we have enantiomers? Okay, so we've got a whole bunch of enantiomer examples up here. At the top, we've got naproxen. Okay, ignore the S and the R for the moment. One of those is an anti-inflammatory. The other one's a liver toxin. Okay, well, naproxen being kind of a painkiller, it might be nice to only ingest the anti-inflammatory. If we take the other enantiomer version, it turns into a liver toxin. That's not particularly pleasant. If we take a look at another fun compound, which we'll see next week, limonene. I don't remember which one's which. Limonene smells of citrus. Okay, it's extracted from oranges. If we look at its mirror image, or its enantiomer, it actually becomes pinene, and it smells like turpentine. It's a pretty drastically different property for those enantiomers. Okay? If we take a look at the last 2, carvone. Carvone smells like mint. The other form of that carvone molecule smells like caraway. So we see extremely different properties coming out of these. But there's kind of an interesting issue that comes out of this. If we look at the standard physical properties, they have the same melting point. They have the same type of forces. Right? Each one. Then how come we can detect a difference between those 2 molecules? Guess what your body is? Chiral. The receptors in your nose that detect different scents, all of those are chiral, which means each of those molecules, being chiral, interact with it differently. It's like, how many of you are left-handed? Left-handed people? Right? Those of you that are left-handed, how many times when you're growing up in little elementary school stuff, they give you the right-handed scissors and force you to use them? Okay, well, how much did it suck to have to use the right-handed scissors? Right, it's pretty awful. It's because scissors are chiral. They're designed for the majority of people. And the majority of people are right-handed. So if you have a school with very limited funding, all of your scissors are right-handed, which means those few of you that are left-handed have to deal with these really weird, awkward-shaped things and try and cut stuff with. Right? Your molecules have this same kind of chirality. Your nose goes through and acts like those right or left-handed scissors and interacts with different things in a slightly different fashion, which is why we acknowledge them as different scents, okay? Or different physical properties when they interact with the different enzymes that are generating the anti-inflammatory or the liver toxin issue. Okay? Our bodies are chiral, so our molecules that are chiral will interact differently with other chiral molecules. But if we take those same chiral molecules and we put them in an achiral environment, we cannot differentiate them. They have the exact same physical properties. So if we go through and synthesize naproxen, and we aren't careful about that chiral center, what ends up happening? Well, we give out a drug, half of the drug cures our pain, and the other half of our drug destroys our liver. That's a bit problematic. Right? So when we go through and do syntheses, we have to come up with ways to avoid this problem. Okay, so how can we separate them? The very first option is you don't make them. You design your synthesis that you never make enantiomers. Okay, so you have to rethink how you approach building molecules to prevent the formation of these enantiomeric pairs. Okay? That can be a bit of a challenge, and there are some cases where you're not going to have a choice, you're going to have to make them. Right? So if you go through and do actually make them, you need to separate them somehow. Probably the easiest way to do it is to separate it on some type of chiral medium. Right? We could use a TLC plate that instead of silica has some chiral molecule on it. Well, that chiral molecule is going to now interact preferentially with one of our enantiomers than the other. That can change how it separates. Okay? The other fun thing that we can do is once we've generated the enantiomers, we can react them both with a chiral pure compound. Okay? If we go through and react them both, we end up generating a new product. Okay? So if we take a look at this first molecule, the relationship between these two structures is diastereomers, you'll find, requires 2 stereocenters, minimally. We only have 1 stereocenter here. These are mirror images of each other. Right? These are enantiomers. Okay. The carbon structures directly overlap. What happens if we change from wedge to dash if our carbon structure is maintained? We're looking at the mirror image. Okay. If we now react this with this molecule, RR tartaric acid, it has 2 chiral atoms in it. Okay. Big old nasty looking structure. So we do this reaction, and what we're going to end up generating is a salt. Okay. The nitrogen from our enantiomer will pick up a hydrogen from our tartaric acid, okay, and become positively charged. The tartaric acid will pick up a negative charge because it just lost that hydrogen. We now have an ionic bond between those 2 compounds. Okay, and this is going to happen equally with both of these compounds. No difference. So we completely react it out. What is the relationship between these 2 structures? Okay, what we can do is kind of just pretend that we connect everything across. The relationship here, what's the relationship circled in blue? They're mirrors. What's the relationship circled in purple now? Identical. And in green? Identical. Are these structures mirror images of each other? No. What is the relationship? They are diastereomers. They cannot be identical. If they were identical, we would see identical at every single one of those positions. At one position, we call them mirror images. So these are now diastereomers. What is special about diastereomers? They have different physical properties. Now that I've generated these different physical properties, I can crystallize one of those in preference to the other. I've now purified and allowed myself to separate between those 2. Okay. Fancy technique, it actually ends up showing up in a lot of pre-med or pre-health type tests, standardized tests. Okay, so be aware of that. We end up generating a new relationship. Okay. Once they're diastereomers, we can now separate them away from each other. Kind of fun. The last thing that we can go through and do with this doesn't really allow us to separate them, but what it does is at least tell us how much we have of one or the other. So we can report the enantiomeric excess. There's a table there. Enantiomeric excess is the percent of the highest enantiomer, doesn't matter which one, minus the percent of the lowest. Okay, so if we have a perfect enantiomeric mixture, what would our enantiomeric excess be? 0. Because it's 50% one, 50% the other. Okay, so what this allows us to do is see what the relationship is between those. Okay? In the case of something like naproxen, we probably want an enantiomeric excess that is darn close to 100%. Okay? Because we don't want the liver toxin, but we want the anti-inflammatory. Okay? So it's just a way of reporting that information. So that's how you go through and calculate it, this enantiomeric excess. Questions? Sweetness. So how can we figure out how much of one we have over the other? Okay, this is where we would look at something known as optical activity. using a technique known as polarimetry. What we end up doing is taking a sodium lamp with a particular light signal associated with that. And we take a filter to kind of filter out a bunch of excess light, so we only get one color. The one color is typically referred to as the sodium D line, because D responds to the light of sodium light that's coming through. Okay, so it's typically some kind of yellow color. Once that light passes through that filter, okay, what they're showing in the middle here is a little bit odd. They're showing all these vectors. What do all those vectors mean? How does light travel? It spreads. It goes out to all directions. We then pass it through this polarizing filter. What happened to the light output? It's only going up and down. We've polarized it. We've removed all of the light that's moving on the whatever axis you want to call that, the x-axis. Right? Is this something that you potentially have already seen in your life? Very likely. Okay? If you have, they're becoming cheaper now, but if you have some money, you can buy polarized lenses. Okay? What is polarized lenses? On sunglasses, it's a polarizing filter. Okay? Why do people like polarizing lenses? You don't have to make them quite as dark, but it removes 50% of the light right away. It removes the light on a different axis, and we only get one version of light. Okay? So what happens if we tip those polarized lenses and say that we're polarized in the vertical direction, and I take a second pair of sunglasses and I turn them 90 degrees? You can't see through it. Why not? Well, the one lens polarized it so they're only going up and down. You took the other lens and turned it 90 degrees. It now removes the rest of the light. Okay? So if you're ever bored, go into a random store with sunglasses, polarized sunglasses, and take them, the two of them, and spin them. Okay? And you will find that there is an angle at which you see no light pass through. And that is because of the polarization of the lens. Okay? So it can cut a lot of that light almost right away, and we don't have to worry about it anymore. When it comes to optical activity, that then means our light is aimed in only one direction, in that up-down axis. So we now take that light and we pass it through our sample. So that's what's happening in this next system. If we have a chiral molecule, that chiral molecule interacts with that light differently than its enantiomer. And what it will do is start to rotate the light. So the light impacts a molecule, says, oh, that's chiral, I'm going to rotate to the right a little bit. It impacts another molecule of that same chirality, rotates it a little more, and a little more, and a little more. The end result is that at the end of that, we can then determine how much the light was impacted by our molecule. Depending on which direction the light was pushed, we can now go through and assign a chirality representation to our molecules. Those two representations typically are referred to as positive and negative. Because what are we looking at? If we had no optical activity, what happens to the light? It stays exactly straight. Nothing changes. So what's its rotation off the starting axis? 0. Okay? So what happens if it interacts a molecule and it rotates to the left? Okay? Or it rotates to the right? What we're ultimately saying is the positive and negative from our 0 axis. So if we end up looking at it and our light shifts to our positive value, we can refer to our molecule as being primarily positive optical activity. If it rotates to a negative degree value, we can call it a negative optical activity. Those two values typically pick up another sequence of names. Levorotatory for rotating to the left, which is ultimately negative if you think of most number lines. And dextrorotatory for rotating to the right, because dextro is right in German. Yes?
So can you use the same sample and get both positive and negative if you just...
So if I take a sample that is only the positive chiral molecule, what's the optical activity I'm going to see? only going to rotate it to the right every single time. If I take a sample that is half negative and half positive, which way does my sample rotate? It won't rotate, because what's going to happen? They will cancel each other out and we see no effect. Right? So an individual sample will always consistently rotate either positive or negative if it has a chiral molecule. No matter the orientation, only because our sample cell is freely rotating. Okay? Everything is liquid, we get free tumbling within that. Okay? So this is kind of neat because now what we have is we could go through and refer to our compound as positive or negative. See, did I actually do that on the tartaric acid? I did not. Dang it. Right. We could also refer to it as, this is where it becomes fun, L or D. You'll notice I use lowercase l and d. Why? Because capital L and capital D means something else entirely. Okay. If you join biochemistry, capital L and capital D are in reference to glyceraldehyde. Yet another way to look at optical activity. Yippee. Okay? So what we kind of pick up out of this is that we now have a way to represent this positive and negative. How can we go through and calculate these? That R and S will make sense in a little bit. Get rid of the R and S. Is if we look at an individual sample, it's going to be dependent on how much it's going to rotate the light. So we can see how much it was rotated. That's our alpha observed. It's also going to depend on the concentration of our sample. Why should that matter? If you've got a lot of red in one spot, what's the color look like? Red. If we have only a little bit of red, it looks pink. Does the concentration affect how we interpret our signal? Absolutely. So why do we fold concentration into this? Because what we want is a standardized way to represent our optical activity. Okay? So we have to include concentration. The other thing that shows up is this L, which is your path length. It's how much or how far did the light have to pass through in the sample. Because the further that length, the more color we end up seeing. So if we took a tube and looked at it from its side, where we had equal concentrations, but then looked at it end on, what happens to our apparent color? It gets darker because there's more stuff it has to pass through. Okay, so we have to evaluate all of these different terms to come through with our calculation. What you will be expected to do, at least on the homework, is just punching in variables and coming up with a calculation. Okay? Not calculations. So this is kind of a common multiple choice question, which is ultimately what you're going to be responsible for. Your homework will have you do some other calculations that I'm not too concerned about, but you should be able to go through and do anyway. And we'll talk about those in a little bit. So where is it important? Which of the following show up? We haven't talked about RNS. We'll come back to this question. Calculations involving optical activity. There are two ways to calculate enantiomeric excess. We have the highest constant. Whoa, I think I just crashed my software. We have the highest percent enantiomer minus the lowest percent enantiomer, which we already talked about. We can also use optical activity. We can take the optical activity of the mixture divided by the optical activity of a pure sample. Okay. If it's a pure sample, okay, if our mixture is now pure, what would the enantiomeric excess be? 100%. Does that make sense? Should it be 100% if it's pure? Yeah. So we can take that information and go through and ultimately determine the independent percentages of R and S. Okay? I will admit right now I will not ask a question on the exam on this because I don't think it's all that important to evaluate. It does show up in the homework. If you've got questions on it, ask about it and I'll help you through it with the homework. Okay? Where we need to get into is looking at nomenclature. We have to be able to refer to our different molecules by different names. So far, the only way we've established this is with positive and negative, which means if you look at the thalidomide on the left, we'd have to go through and run an experiment. Is it positive or is it negative? Okay, by looking at how it interacts with light. Is that something you could do easily on a test? No. So we need some other way to differentiate these two compounds. That way to differentiate them goes back to something known as the Cahn-Ingold Prelog rules, which you will undoubtedly forget, at least the name of, but it gets referenced every so often. So I'll repeat it again. Cahn-Ingold Prelog rules. What these rules apply for is determining R and S. Okay, it is the absolute configuration. So looking at a structure, and only the structure, you can now determine a nomenclature system for R and S. Which one is which? Does this tie back to optical activity? As an optical activity, if we had one molecule, the light rotated, say, left or right. Can I use the negative and positives that we've got in optical activity to match to the R and S of the Cahn-Ingold system? We would really hope so. It's not true. They are two entirely separate systems. Okay? So if you have something that is positive, that has no bearing on whether that molecule is named R or S. Entirely separate systems. Okay? So what are our Cahn-Ingold Prelog rules? Okay? They look a bit long and extended. They really aren't that bad. It's pretty much the same thing that you go through and do with cis and trans. Our first step is to identify a chiral carbon. Okay? There's no point in looking at the Cahn-Ingold rules if you don't have a chiral carbon. So first find that chiral carbon. Once you've found it, you have to go through and assign priorities to each of the 4 different groups attached to it. Okay, so we've been going through and numbering our groups 1 through 4 so that we know where they are. Be careful now. Okay? Now you have to actually assign a priority on 1 through 4. The standard notation is that 1 is the highest priority. 4 is the lowest priority. As long as you are consistent in how you use the rules, that ultimately does not matter. Just realize we will always talk about it as 1 highest, 4 lowest. How do we assign priority? It all goes back to atomic mass. The higher the atomic mass, the higher the priority. Right? What if there's no difference? You move to the next atom. Right? And again, evaluate atomic mass. There's still no difference. You move to the next atom. Right? Again, you compare atomic mass. If there's no difference, you go all the way through and you find no difference, then what does that mean? You picked the non-chiral carbon. Try again. Okay? So those steps of acknowledging and finding chiral carbons quickly is very, very important to being able to process these things. Once you've assigned all of the priorities, you now have to look at the molecule in a very particular fashion. Okay? You must have the molecule oriented so that the lowest priority group is aimed away from you, which means your lowest priority group has what bond structure? Dashed. Why? Which direction is my hand turning? Now which way is it turning? Okay, I did not change the rotation of my hand, but if we change our perspective on the molecule, we get to a different conclusion. Okay? These are just like all your other nomenclature rules. You must look at the molecule in this fashion. Otherwise, you are going to get the wrong answer. So once you've assigned your priorities, you orient the molecule such that the lowest priority is aimed away from you. So what we've done in this first case is we took our tetrahedral structure and we've moved it into a pseudo-Newman projection, right, where atom number 4 is aimed away from us. We then have 1, 2, and 3. So if we drew on the eyeball, we'd be looking right about there. Still, it looks kind of like an eyeball. Once you've got that orientation, draw an arc between point 1 and 2, 2 and 3. Which direction are we turning? And that case, we are turning clockwise, which means we assign R. What happens if we do a subtle change in our structure? Notice the difference between these two. If we're again viewing our molecule with our sketchy looking eyeball and lashes, okay, what happens when we go through and do that change in view and we look at our Newman projection? 1 to 2, 2 to 3, which direction are we turning? Counterclockwise. So our counterclockwise carries the S assignment, our clockwise carries the R. Not to be confused with the direction that light rotates. Because if light rotates clockwise, it becomes positive, which has nothing to do with R and S. Okay? So you have to try and keep those two systems separate from each other. So here we got a whole bunch of examples to take a look at. Let's go through and work a couple. Because presumably you need some work with it. Okay, that's good. That's what I figured. We've got our chiral atom here. We've already done this problem, right? So we've identified that chiral atom in that lower left. We now want to go through and assign priorities. Okay. Up to you how you want to go through and approach it, but I tend to approach with the most obvious ones first. The most obvious one to me first is going to be hydrogen being the smallest is 4. We now run into an issue. What's that issue? Carbon to carbon to carbon, and we have an extra issue. We have the double bond. When we go through and assign our priorities, they can only be assigned to sp3 atoms. Is the carbon of our double bond sp3? No. So what we're going to do is use some phantom carbons to make it sp3. Okay, I know everybody loves this. Okay, phantom carbon. Our carbon is bound to what? What things are attached to it? Top one. We've got a hydrogen, we've got a carbon, and another carbon to account for that second bond. Where's our phantom? Just draw it on. Okay? Why does this become helpful for us? Well, if we now look at what happens to our other ones. This carbon versus that one, our purple carbons. Which one is higher priority? The top one becomes the higher priority because it's bound to more carbons. Which is higher priority? The bottom because bound to more carbons. What does that tell us? Our CH3 is 3. So now for the challenge. Which is higher priority? Why the top one? It's bound to more carbons or less hydrogens, that works, which means it gets the higher priorities. I've been coloring in red. We call that one 1, this one 2. What do we now have to do? Orient the molecule so that our lowest priority group is aimed away from us. What was that? Go ahead. It is already aimed away from us. If you've drawn your structure according to the proper three-dimensional characteristics, you do not have to do any more drawing. 1 to 2, 2 to 3, which direction are we turning? Okay. Where are we viewing that? You're kind of viewing it kind of here, as best we can draw it. Okay. We do another one?
Yeah.
One of the top ones? Okay. Yeah, oh, no, come back here.
What's it mean that it has S? What is that?
So what that means is that the arrangement of your groups is in the S arrangement. So if I was going to go through and name this compound, we have a cyclohexane. Whoops. Cyclohexene. Okay. Where's the ene show up? Which is our highest priority functional group? The double bonds. The double bond by definition shows up at position 1. We have a methyl as a substituent. Where does the methyl show up? Careful when you number with your alkenes. You number through the double bond. So it shows up at the 3 position, 3-methyl cyclohexene. Okay. Problem with this is that we have a chiral atom at position 3. We need to make sure that when we draw this structure that that methyl group is aimed up, at least in this orientation. How can we ensure that the next person to draw this will draw it up? We need to include that R and S into it. This one was, I already forgot, S, so we can include the S. But where was it S? At the 3 position. So it is commonly referred to as 3S, 3-methyl cyclohexene. Okay. Nomenclature with R and S's are a bit obnoxious. Why was I avoiding the top examples? There are 2 chiral atoms, which means when we go through to name this, we have to name both of them. So let's go through and evaluate the harder of the 2, and then we'll end. Take a look at that. What do you see first? And we're calling this our red carbon. What's that? See the hydrogen? What's the priority of our hydrogen? Lowest. There's 4. What else do you see? Chlorine, which is going to be 1. We can now move out to carbon versus carbon. Is there a difference? I can accept both yeses and nos. Okay. If you're saying no, what do we have to do? Move out to the next furthest atom. Kind of up to you where you go, but you typically move out to the highest molecular weight atom, which means I'm comparing chlorine to carbon. Is there a difference? Yes. Which one takes priority? Chlorine takes priority, which means what about this carbon? Higher priority than the other, so it gets assigned 2. The other one is 3. Questions? If we now assign optical activity, we can connect 1 to 2, 2 to 3, and we would say clockwise, and we would say R, and we would be wrong. Why would we be wrong? The lowest priority must be aimed away from you. Where's the lowest priority in this case? It's wedged, aimed at you. Okay? So if the lowest priority is aimed away from you, it's straightforward and deliberate right away. If it's aimed at you, it's also straightforward and right away answer. Why? What happened to the rotation of my hand as you looked at it from the other side of me? It's opposite. So as long as we acknowledge that we're looking at it from the wrong view, if that looks like it's rotating clockwise to the R, that means we must switch it to S. There's our answer. For 1 chiral atom. Now what do we have to do? Now you have to do the other one. Okay. Quickly, 1, 4, 2, 3. Our rotation in this case is counterclockwise. I have S. If we're going to go through and name this, we would have 1S, 2S, depending on how nitpicky you want to get, typically you would write in your 1,2 dichlorocyclopentane. Just because we're out of time and we might as well throw some more random stuff in here. What's the relationship between those two structures? They are enantiomers. If you don't see that right away, that's okay. They were drawn in such a way to make it less obvious. Those two are enantiomers of each other. If we go through and look at the name, what's our name going to become?
1R, 2R.
Why'd you say R's?
Because they'd be mirror images.
They're mirror images of each other. So if we know what one is named, we know what the other one is because of that enantiomeric relationship. So we end up with 1R, 2R, 1,2 dichlorocyclopentane. We'll be moving into spectroscopy, which is even more of a mind meld, on Wednesday. Okay? You need to watch the spectroscopy videos. The only thing we will be talking about is kind of the nitpicky subtleties that you can run into when solving spectroscopy. That's what will happen on Wednesday. Next Monday, the plan is to